Experiments in superfluid helium-3 at the very lowest possible temperatures. Really, I'm going to be talking about phase transitions, phase boundaries, defects that exist in the order parameter structures, and whether they may or may not have implications for cosmological models. And just before I carry on, a boojum, for those that don't know, is superfluid helium-3 code for a zero-dimensional or a point defect. Okay, so many people involved in this work. We're quite a large team at Lancaster now. Today I'm going to be concentrating mainly on the thesis work of Matthew Fear and Hazel Martin. The obligatory note from our sponsors, and I wanted to point out this network, CosLab, Condensed Matter in the Cosmology in the Laboratory. We had a series of conferences where condensed matter physicists, hydrogen physicists and cosmologists got together. They looked at our experiments and told us whether there were any cosmological implications or not. Okay, I'm going to give a very brief introduction to the superfluid order parameters, our quantum vacuum states, hopefully give you enough information that you can understand the experiments that I'm going to talk about. I'll talk about an experiment which is potentially an analogue of brane anti-brane annihilation. I'll talk about a new defect structure that may have spawned, which we don't think has been seen in helium-3 before, but we've not been able to prove it's a new defect yet because we have to do some new experiments to show what the properties of this defect are. Okay, so helium-3, a Cooper pair. It's a fermionic condensate. Because helium-3 atoms have structure, they have extent, they have to orbit around each other, they can't share the same space, so the orbital angular momentum has to be at least 1. To preserve overall antisymmetry of the wave function, that means the spin is 1, and that gives you a huge number of degrees of freedom about what various order parameter states you can build from these Cooper pairs. Okay, so what does it choose? Yesterday you saw this phase diagram in George Pickett's talk. It's normal liquid helium-3 at 0 bar, at 1,000th of a degree of absolute zero. It goes into the B phase of the superfluid. What I'm going to talk about today is another axis on the phase diagram. We put a magnetic field on and a critical field that will induce a transition to the A phase of helium-3. Normally you have to put pressure on to get the A phase. We're going to induce it with a magnetic field. Because you can control and shape magnetic fields, then you can control and shape this first order interface between the A and the B phase. Again, that's our kind of proto brain. So these experiments all take place very low pressures, 0 bar or thereabouts, and around 150 millionths of a degree above absolute zero. Okay, so it's all about broken symmetries. I think everybody in this room knows more about the top part than I do. What I do know about is superfluid helium-3. It's a symmetry-breaking phase transition. The order parameter wave function has a phase. The orbital angular momentum chooses a direction, and the spin part of the wave function chooses a direction. Okay. This is how we talk about the A phase and the B phase. So what you've got here is you've got the central sphere is the Fermi surface, where the condensate lives, and then you have an energy gap structure where to break a Cooper pair you need to put in energy to take it out of the condensate and create quasiparticles. You're probably used to an S equals 0 superconductor where this energy gap or order parameter structure is isotropic in momentum space. It turns out that the A phase of helium-3 only has up-up spin pairs and down-down spin pairs, and the consequence of that is that you have nodes in the gap. You've got directions in momentum space where it costs no energy to break a Cooper pair, so they're full of quasiparticles. That L direction in momentum space actually lines up in real space, and it forms a liquid crystal-like texture in the superfluid. So if you're moving through the A phase and the L direction is pointing in the Z direction everywhere, it's superfluid in the XY direction when you move. There's no friction, but as soon as you start to jump up and down, you're interacting with a normal fluid. It's a really strange superfluid. And we can play with this L texture. It likes to lie perpendicular to a magnetic field. It lies perpendicular to a solid surface. It also lies parallel to the interface between the A phase and the B phase, which I'll come on to later. So it turns out it's impossible to fill an ordinary container with the A phase of helium-3 and satisfy all the textural constraints without there being at least one defect in that L texture. Okay, the B phase has all three spin components, up, up, down, down, and up, down. It ends up in low magnetic field looking very much like an S equals naught superconductor. There's an isotropic gap in every direction in momentum space. We're going to mess that up by putting a magnetic field on. A magnetic field will suppress the up-down spin pairing because they can't be magnetized. The result of that is that you squash the energy gap along the direction of the magnetic field. So you've created another L direction. So you've created the possibility of another texture in the B phase of the superfluid. This L direction, it's along the magnetic field, unlike perpendicular to the magnetic field in the A phase. It also lies perpendicular to the walls, and it also lies parallel to the AB interface. So what's so special about this first order transition between the A and B phase? So of course, the first thing is it's extremely pure. Almost everything is in the condensate. We don't really need to worry about this hypercooled, but just to point out, it's a really good first order transition. There's a latent heat associated with it. There's a surface tension. There are meniscus effects. You can look at the wetting of the A phase against the wall over the B phase. It behaves like a really good first order phase transition. Apart from nucleation, Henry Tai has just published a couple of papers about a potential cosmological model to overcome the nucleation problems in helium-3, which I'm not going to talk about in this talk. And Henry called it a dirty secret, and it is the dirty secret of helium-3. I love talking about dirty secrets, so if anybody wants to talk about that afterwards, come and talk to me. But we're going to talk about the phase boundary between A and B. Now, it's not like you have the A phase order parameter, then the B phase order parameter, and some horrible discontinuity in between. It actually transforms coherently from the A phase through another quantum vacuum state or superfluid order parameter, possibly the B phase, the planar phase, no one's sure, then into the B phase. So it's a coherent ordered interface. So what you've got, if you can imagine, you can have a field gradient where you've got A phase in the high field, B phase in the low field, you have planar phase in between. You've then got a three-dimensional background vacuum state which contains a two-dimensional vacuum state within it. It's all starting to sound a little bit similar to a brane embedded inside a space of higher dimension. Okay. So is it a good analogy for a brane? What are we going to measure? We measure the excitations. So in the B phase, there's very few excitations at low temperatures. You get a Boltzmann distribution of broken quasiparticles. In the A phase, there's lots of quasiparticle excitations at the nodes because it costs no energy to break a Cooper pair. And I won't go into the details, but essentially we have devices which can create these quasiparticles and can measure the density of these quasiparticles, thermometers. Okay. So this is a picture of the end of the cell. Basically, the fridge that this takes place in would almost fill this whole room, and it's all about getting this very small tube that's about the size of my little finger full of superfluid helium-3 at 100 microkelvin, maybe 200 microkelvin sometimes. And these are our devices that create these quasiparticle excitations and measure them. These are vibrating wire resonators. I'm going to show you a different tool we're using later. And this tube sits inside a stack of superconducting solenoids that we use to create and shape and control the magnetic field and thereby move the AB interface around. What we're going to do in the simple experiment is we're going to create quasiparticles at the bottom, fire them up the tube, and measure the impedance to quasiparticles as they go down the tube. Basically a transport measurement. Then we're going to mess around with the order parameter in between and see if that impedes the transport. Okay. So the shaped magnetic fields, what this experiment was first designed for was to create a bubble of B phase completely surrounded by the A phase. The reason for that is actually to probe this dirty secret of nucleation. And what we discovered while we're attempting to create this bubble and characterize it is this event. So we put the A phase in, it forms a sandwich between two pieces of B phase, then we take it out again, we measure the impedance before it went in, we measure the impedance when it's in there, and we measure the impedance when it comes out. And this was the surprise. So before, this is just a plot of the excitation impedance, and this is just the temperature as it slowly warms up. For temperature, read time, and you've got about 12 hours along the axis. So before the A phase went in, the quasiparticles were impeded going down the tube. There are some reasons for that that are outside the scope of this talk. We put the A phase in, the energy gap structure changes. We've put basically two interfaces in there, a B to A and an A to B. That bounces the quasiparticles back down the tube, and we measure some impedance. When we then take the A phase out again, we expected it to come back to where it started, but it didn't. It continued to have some impedance. It had some memory that the A phase, or rather the two AB interfaces, had been in the experiment. So we posit that it must create topological defects, this annihilation, that can impede the quasiparticles. Okay. So textures, to start with, are already very complicated. So this is the nicest texture we think we can get in that cylinder before we start. So what you've got, these black arrows represent the L direction in the B phase, the L direction in the A phase. In order to satisfy as many of the boundary conditions and constraints on the texture as you can, you have to have at least one line defect in the A phase. And this has to end on two zero-dimensional defects on the AB interface. Okay? So that's your boojum. And the boojums are two different types, a radial boojum and a hyperbolic boojum, which depends on the way the L direction enters and leaves this zero-dimensional defect. So that's a two-dimensional picture. But actually it gets even more complicated because it turns out that this boojum on the AB brane extending into the B phase has to extend with a hardcore vortex. It also turns out that the L direction in the A phase next to the interface and the L direction in the B phase next to the interface have to be perpendicular to each other. So in 3 dimensions, it looks something like this. Okay, so we start with not just clear and pure AB interface. There are already some defects in the texture of the superfluid before we do the annihilation. So this is boojum and a hardcore vortex going to the B phase. So here's our cartoon for what happens. We think that we put the A phase in, we create at least one of these type of defects. The vortex lines will try and reduce in length. They'll pull this defect to the side. Then when we remove the A phase, the two interfaces come together, they pinch off in the middle, and the surface tension rips that apart to completely remove the A phase from the cell, and we must create lots and lots of defects in that process. What are they post-annihilation? Let me first say we don't think they can possibly be more hardcore vortices with a flow, because they would move away from this region in our cell and they would decay over time, and we don't see that. We don't think it's a two-dimensional defect left behind by the interface, because we don't measure the same extra impedance after every annihilation event. We always measure some extra impedance, but it's not always the same, and a two-dimensional object would give you the same impedance every time. So we've had to come up with a new type of defect which lives in this high field distorted B phase, which interestingly does not have any mass flow around it. It doesn't behave like a normal vortex that you're used to in helium-3. So if we start with the L texture going into the cell wall, we put a boojum on there, flip round the L direction, we extend this boojum texture out into the bulk, but we rotate the L vector uniformly in the blue plane. All these are nice, okay things you can do to the B phase within the helium lengths in the system. Okay, and it ends up as a hyperbolic boojum on the other side. So it's a line defect with two point defects on either end, and it gives us exactly what we want. Because we've rotated the L direction, we've changed the size of the energy gap that the quasiparticles see, and we will therefore see an increased impedance to the transport of quasiparticles down the tube. Okay, next step. I'll try to get through this quickly. One of the problems with those vibrating wires that have been used, it's a remote probe. We're able to measure transport. We heated up the bottom of a tube and we measured how hot the top got in response. We were not able to probe directly the interface itself or the annihilation region. So we've got a new probe, it's a quartz tuning fork. These are the tuning forks that are the timing piece in your watch. They're also damped in helium-3. It turns out they're sensitive to having their momentum removed by these quasi-particles. We've got a new tube. This is a look down it. We've basically projected a lot of these tiny quartz tuning forks through the side walls of the test tube. It's about a few millimeters long, and the tines on the tuning fork are about 0.5 millimeter, 0.4 millimeters apart. Okay. So we haven't got as far as doing the annihilation again. What we have done is we've moved the AB interface past these forks. I'm going to show you what we see. Basically start low field, high field at the bottom with A phase, low field at the top, increase the current to your solenoid, the interface will move up. I've got a cartoon of what's happening alongside real data. So the fork starts out in the B phase, the interface is approaching it, continues to approach, approaches. What we're going to see is a little jump as it starts to approach. Okay. We'll see it past the first tine of the fork, second tine of the fork, and then it's in the A phase at the end. Okay. So that's a mechanical object sensing the passage of two different superfluid order parameters at 150 millionths of a degree above absolute zero. Okay. And this damping axis, you can relate that to the number of quasi-particles it's measuring. So it's higher in the A phase than it is in the B phase. So you do this many times. What we're excited about in this measurement is not only can we see it pass the two fork tines, but we always see the resolution's not good, this is improving. We see a small bump as the interface approaches the tine. I think we're sensitive to the bending in the texture close to the AB interface. We're seeing those defects trying to arrange themselves around the AB interface. And afterwards, everything relaxes to about the same damping inside the A phase. But before that, all hell breaks loose. I think that's the texture in the A phase moving around in response to the fork and also trying to find its equilibrium position afterwards. So the future prospects, we're going to use these tuning forks to probe these defects in the high field annihilation region. That bump just before it passes the tine, it tells us that it's sensitive to a small rotation in the order parameter of the B phase. So these forks should pick out this defect because all that defect consists of is a small rotation in the B phase order parameter. And ultimately, we want to look at this B phase bubble confined by A phase. And so I'll finish there.
Questions? Yes.
Why is it necessary that there's, when you form the A phase, that there's a defect in there?
Yeah, so it's like it's what do they call it, the hairy ball theorem. It's the same reason you can't comb the hair on a sphere all the same path without leaving a defect. In the A phase, when you put it in a three-dimensional container, this L direction has to line up in such a way that you just can't comb it all perfectly. So that there has to be some kind of defect joining your two branes before they even come together.
And is it possible to observe different phases except A and B phase?
So we think that the phase between the A and B is the planar phase. We're not sure. So it goes from the A to the B phase over a few coherence lengths, which is is a few hundred nanometers. So if we had an object smaller than the tuning fork that we could measure the damping on that kind of length scale, we think we could potentially see right into the interface. What we're trying to do with these forks is that, for instance, they're across the cell. We're trying to grab the interface by the forks, wobble one, and see what we measure on the other side. And the transport of quasi-particles through that interface should tell us whether it's A phase-like, B phase-like, or a new phase. But people are also doing experiments where they confine the superfluid in very thin plates, and then measure what they think is a planar phase there as well.
I only would like to mention that what I yesterday talked about, Biancan experiment with A phase, which is swallow in B phase. I see that such things exist in principle, possible exist.
Well, yeah, it's much easier to put the B phase inside the A phase than the A phase inside the B phase.
So it's possible.
Yeah. We have done it, but we never published it because we're sure that we made the bubble. It was difficult to interpret our results to say that.
Okay, I ask you later. Thank you.
Briefly, as there is a trusted Ginzburg-Landau theory for superconducting helium-3, okay? Well, and your geometry is quite simple. I think it's worthwhile trying to model. I mean, full Ginzburg-Landau, not just kind of locally near A and B phases. Yeah, so.
Welcome to try, Andy.
Pardon?
You're welcome to try.
No, I mean, somebody in this room, I'm sure, would like to try. I mean, actually, all equations are known. Yeah.
Not in the Ginzburg-Landau region. I mean,
It is, but I mean, with the full degrees of freedom of all the parameters. Just 18 real numbers.
That's all.
Just 18.
Thank you again.